This is AP Calculus BC, and in this video, I'm going to start talking about our next unit, which is going to be all about integrals. And in this section, or these two sections in particular, we're going to talk about just the general idea of an integral, and we're also going to start talking about what we call an indefinite integral. So this first section in your book is relatively straightforward. What it really is just trying to get you to understand the main idea behind what we're doing when we find an integral of a function. And I'm not going to spend a lot of time on this section because you can read through the section and you can work through the examples. Really working through the examples will help you understand this more than anything else. But I just want to give you just a general idea of what we're doing here. So typically when we interpret an integral of a function, and this is really when we're talking about what we call a definite integral. A definite integral corresponds to the area underneath a function. If I integrate the function f of x, the result of that integral is the area underneath the function, or the area between that function and the x-axis. So when we do this, what we're really doing is a rectangular approximation. And you see these side-by-side graphs here. So an integral is actually a limit, and we'll get into that in a couple of days when we get more into this whole idea of approximating with rectangles. But if you notice here, what we're trying to do is find the area underneath this f of x curve from the points A to B. And at the beginning, the first graph on the left, there are 5 subintervals there. There's 5 rectangles that we're trying to use to approximate that area. On the next graph, it looks like we've doubled it to 10, and then you can see on the graph on the right that now we're starting to get a lot of rectangles. So in reality, what happens is when we are trying to find the value of the integral, we're taking the limit as the width of each one of those rectangles approaches 0. So essentially what that does is create an infinite number of rectangles that can then not just approximate the area underneath the curve, but actually our solution will converge to the actual area underneath the curve. So that's really the idea of it. We'll do some things as we go through this unit where we go through and actually work some of these with rectangles to get a feel for what's happening. And then eventually we'll just get into the whole idea of just solving these with antiderivatives. When we talk about the next section and we do indefinite integrals, that's what we're going to do, is start talking about the antiderivatives, which will be part of the process of solving a definite integral. Okay, so you can see down here, there is a method that we can actually use to find this area, but we're a couple of days away from that. So for today, what I really want to focus on is section 5.2, which is the indefinite integral. And when you think of an indefinite integral, you can sort of just think of it as the antiderivative function. And essentially what we're going to do here is look at the relationship between a function and a derivative, or a derivative and its antiderivative, which is just, when we say antiderivative, it's the opposite of a derivative. So you notice here with this notation, it says the function f of x equals 1/4 x to the 4th is an antiderivative of x cubed. Because if I were to take the derivative of this f function, and the f function that I'm talking about is this one here, if I took the derivative of that function, I'm going to get x cubed. Now, the thing that you have to be careful about here is when we start talking about antiderivatives, there's actually an infinite number of antiderivatives for any derivative function that we have. And we'll get into a little bit more of that, the details of that here in just a minute. Okay, so let's look at an example. Now, notice the notation that we're using here in this example. We have a lowercase f of x and an uppercase f of x. We haven't really used this notation a lot, but when you see the lowercase f of x in comparison to the uppercase f of x, the lowercase would be the derivative of the uppercase f of x function. Okay, so we're looking at a derivative function and we're trying to find the original function. So all we're going to do is actually just do the opposite of taking the derivative. And there's actually a power rule for this, which we'll talk about in just a second. But the way you're thinking about this, when you look at the derivative function, we're looking at these terms, we're trying to think, okay, if I ended up with 3x squared, what was the term in the original function? And it turns out it was x cubed. Or if I end up with 4x, what was the term in the original function? It would have to be 2x squared. For a -5, it would have been -5x. And then the last part of this, I'm going to put in here plus c, where c is some arbitrary constant. Now think about that. If you had any number there for c, whether it be 1 or pi or -5 or 1,000, when I take the derivative of a constant, it's going to turn out to be 0. So there's no way for me to know what that constant is when I do an antiderivative unless I have more information provided for me so that I can solve for that c value. Okay, so whenever we do an antiderivative or solve an indefinite integral, we always have to include that plus c because it's the difference between a single solution. If I leave the c out, I'm essentially saying c is 0, so that would be one unique solution. Or if I have the plus c, that's an infinite number of solutions. So it's a really big thing to leave the plus c out. The difference between one solution and an infinite number of solutions is obviously very, very different in terms of the interpretation. Okay, so when we go through this, there are some antiderivative rules. Now, you don't have to remember these rules because you already know these rules. All they are the opposite of the derivative rules. So if you go through this table and you look at these, formulas that they're calling them, all they are is undoing the derivative rules that we've done. Now, the only one that you might want to look at a little bit here is the one for the power rule. That's the one that we're going to use the most. Remember, when we do the power rule, we bring the exponent down and then we multiply, or we change the exponent to whatever it was, -1. Well, when we take the antiderivative, which is what we're doing here, we have to do the opposite of that. And notice if we have x to the r, we add 1 to the exponent and we divide by the new exponent. So that's the most common antiderivative rule, or if you want to call it an integration formula, it's the most common antiderivative rule that we're going to use. Now, the rest of these, I'll let you look at them on your own, but you will notice that they are essentially just the derivative rules in reverse. Okay, so let's take a look at a few examples. Now, this is integral notation. When you see an integral like this, it sort of has the shape of an S, and it's because an integral is actually a summation. If you think back to what we did, what I was talking about in section 5.1 with all of the rectangles being added together, when we do a definite integral, it is a summation. When we do an indefinite integral, we're essentially doing an antiderivative. Now, there's some notation here that you're going to see. So notice that we have this integral symbol that's telling us that we're going to take the antiderivative, and then you've got this dx. So when it's an indefinite integral, that's essentially telling us what are we going to integrate with respect to. So in this case, I'm going to integrate with respect to x. So that means that when I'm thinking about how do I do my antiderivative, it's just work with the x terms and do the opposite of taking a derivative. So for example, for this first one, I'm going to add 1 to the exponent, divide by the new exponent, and then add c, because I don't know if that c value is there. I don't know if it was 0. I don't know what it possibly was. So that would be my solution for that indefinite integral. Notice these are really easy to check. If I took the derivative of that result, I would end up with x to the 9th. So it's very, very easy to make sure that you've done these correctly just by reversing the process that you just did. Instead of taking the antiderivative, take the derivative and check your answer. Okay, so I've got a few here for you to try. And what I want you to do is just take a minute, work through these. None of these are difficult, but work through these. And I want you to pause the video, take 2 or 3 minutes, work through these. And then when you unpause it, I will show you the solutions to these problems. Okay, so here's the solutions that you should have ended up with. You can see with the square root of x, I just made that x to the 1/2 and then just, again, applied the power rule. With the 1 over x cubed, the easy way to do that one is to think of it as x to the -3 power and add 1 to the exponent, divide by the new exponent. You can see I got -1 over 2x squared plus c. Now, the 1 over x, that one's a special case. Remember, we have to be thinking about what function has the derivative of 1 over x, and that is the natural log of x. The other thing is I want to make sure that I include the absolute value in the natural log because I don't have any domain restrictions on this part of the problem. They didn't tell me that x is restricted to be greater than 0 or x has to be less than 0. So I need to make sure my antiderivative function applies for all values of x. Okay, and then you see the result for negative cosine x. Antiderivative is negative sine. And for sine x, the antiderivative or the indefinite integral is negative cosine x plus c. Okay, so relatively simple to do. Now, these are going to get a lot more complicated as we go. And in fact, in the second semester, we're going to get into some pretty advanced integration techniques where these are going to become much, much more challenging. Okay, so there are some properties for indefinite integrals. Keep in mind an integral is just a limit. So the same properties that we've been seeing with limits and derivatives are also going to apply now that we're working with integrals. The whole idea that when I have something multiplied by a constant or my function multiplied by a constant, that constant doesn't have any impact on my antiderivative. I just have to remember to multiply the constant to the antiderivative function. I can integrate terms separately. I can also integrate terms separately if they're subtraction. So those are all properties that we've seen, and those are just intuitive, but those are the properties actually stated out. Now, sometimes you're going to see notation like this. I'm going to show you this example. When you have more than one term, sometimes what you'll see written is you'll see notation with parentheses like this. You can use those, and a lot of times I do. I kind of prefer to have the parentheses, but I left them out here because I wanted to make it really clear. When you're writing an integral out, this is essentially the opening side of your bracket, showing that whatever comes after this is my function, and then this is the closing of your bracket. So everything that's between the integral sign and that differential expression, those terms are going to create the function that I'm trying to find the indefinite integral of. And when you solve a problem like this, all you're going to do is just go through it term by term. So for this, I would have x squared over 2 plus x to the 4th over 4. Remember, I'm just adding 1 to the exponent and dividing by the new exponent, and then plus c. Okay, so really simple to do. Here's another one, same idea, 5 sine x minus x squared. So I want to think about what's the antiderivative of sine. It would be negative cosine. So I'm going to get negative 5 cosine x minus x cubed over 3 plus c. Now the nice thing is, since we're just starting on these integrals, most of your problems where you have to solve the indefinite integral, they're going to be about that simple. There's not really anything difficult about them. Okay, so let's talk a little bit more about this whole idea of the plus c, because the last type of problem that we're going to deal with is going to really revolve around why the plus c is important. So what we have here is a set of the curves that could potentially be the solution for this integral of x squared dx. So you can see when you solve this out, we get 1/3 x cubed plus c. Like I said before, the c can be anything. So over here on this graph, we've got 5 sample curves. Those are 5 of the possible graphs that would follow the rule 1/3 x cubed plus c. Now, like I said before, c can be anything. So really, there's an infinite number of those curves. They all kind of look the same, but the c is going to shift them up or down to a different location. Okay, so let's take a look at solving some of these problems and talk about how do we know what the c needs to be. Okay, so when we solve these problems, sometimes they're going to be presented as differential equations. Differential equations are just equations with differentials in them. We've talked a little bit about that before. But when you see these, and you see these differential equations, for now, I just want you to think of them as functions you're going to take the antiderivative of. So for example here, we have df dx is e to the x plus 20 over 1 plus x squared. And it says if f of 0 is equal to negative 2, so we want to solve it. So when we do this, we're going to start by taking antiderivatives. So I'm going to start by writing my antiderivative function, which would just be f of x. Antiderivative of e to the x is e to the x. Antiderivative of a 20 over 1 plus x squared. Now, when you're working these problems, keep in mind we're only doing basic antiderivative rules here. So whatever expression you see, you should be thinking about what function has a derivative that looks similar to that. If I were to factor the 20 out, I would have 1 over 1 plus x squared. Well, that's the derivative of the inverse tangent of x, and then also don't forget your plus c. Now, notice they gave us a point this time. This is what we call an anchor point. So it's an anchor point because remember that graph we just looked at where there were an infinite number of curves? Well, this anchor point is going to force my graph to be placed into a certain location. I know I want the solution curve that follows that differential equation, but it has to go through the point 0, -2. Well, if I use that point, I can solve for that c value. I know if I plug 0 into my antiderivative function, I'm going to get e to the 0 plus 20 times the inverse tangent of 0 plus c, and that's going to give me a result of -2. Well, think about the values that we have here. E to the 0 is 1, 20 inverse tangent of 0 is 0. So essentially we have 1 plus c is equal to -2, or c is equal to -3. Okay, so in the end, I've got my solution as e to the x plus 20 inverse tangent of x minus 3. And that would be the solution I would want to give since we were given that anchor point. When you work these kind of problems, and we'll talk about this, we have a unit on differential equations in the second semester, but when you work these types of problems, this is referred to as the general solution. And the reason that's the general solution is because I have the plus c in there. There's an infinite number of curves, but these are all the possible curves that have the differential, have the derivative function e to the x plus 20 over 1 plus x squared. This solution that I have boxed in, this is called the particular solution. So it is the particular solution that goes through the point that we were given. So you'll hear me often refer to a general solution. I'm talking about the solution with the plus c, and then the particular solution is obviously the point that, the curve that goes through the point that we're given. All right, so there's two more of these problems that I want you to try. So I'm going to have you pause the video, take a couple of minutes and work through these, and then when you unpause it, I will show you the solutions. All right, so here are the solutions that you should have ended up with. You can see on this first one, I just went through and did the antiderivatives. So when I'm thinking about how am I going to find f of x, I'm essentially, and I don't even usually write this step, but I'm essentially just solving this indefinite integral, the integral of 4 sine x plus 2x to the 4th minus x to the -1/2. So notice my notation here. I told you that I tend to prefer this notation. I included the parentheses here, even though they're not necessary. That's up to you if you want to do that or not. But then from there, I just did antiderivatives. Notice I have a plus c that showed up here. And then I just said, okay, well, if I plug 0 into this function, I know I should get 5. What does c have to be to make that true? And c has to be 9. So in the end, I got my particular solution of -4 cosine x plus 2x to the 5th over 5 minus 2x to the 1/2 plus 9. Okay, so these are really not that difficult to do, provided that you've got a good feel for the antiderivative rules. All right, and then here's the last one. Now, the last one was a little more difficult because it gave you a second derivative. And if you notice here, the information that you're given, it's 2 points that the original function has to go through. And the reason that 2 points are important is because when you start solving these out, or start solving this out and getting back to the original function f of x, you're going to find that you have 2 unknown values. There's going to be a c and then a second arbitrary value that you're going to have to find. Okay, so first thing I did was get my antiderivative to get my f prime. So notice I have a plus c. I don't know anything about the derivative, so I don't have anything that will allow me to solve for c right now. So then I took the antiderivative again and got the original function. But notice that I have a plus c times x, and then I have a plus d here. You don't necessarily have to use c and d, but you need to make sure that you distinguish between those constant values. So I don't want to have plus cx plus c because those values are not necessarily the same. So I need to give them the opportunity to be different by assigning them a different variable. And now when I do that, when I do actually solve for c and then solve for d, sure, they could turn out to be the same, but at least I haven't forced them to be the same no matter what I do. Okay, so we've got 2 unknown values. We have 2 points that we were given. So the first one, f of 0 is 4, made it really easy to solve for d. And then once I knew what D was, I plugged that in here for D, and then I just plugged in f of 1, and I knew that I should end up with 1 when I do that, and that allowed me to get the C value, and now I've got my particular solution. Okay, so you're going to see a lot of these types of questions on the assignment. It's primarily just practicing with those antiderivatives, but also this idea of working from the general solution to get the particular solution.